The man who harnessed infinity. About 200 years after Zeno pondered the nature of space, time, motion, and infinity, another thinker found infinity irresistible. His name was Archimedes. We've met him already in connection with the idea of a cycle, but he is legendary for many other reasons. For one thing, there are a lot of there are a lot of funny stories about him. Several portray him as the original math geek. For example, the story of Plutarch tells us that Archimedes could become so engrossed in geometry that that him forget his food and neglect his person. That certainly rings true for many of us mathematicians. Meals and personal hygiene are not top priorities. Plutarch goes on Plutarch goes on to say that when Archimedes was lost in his mathematics, he would have to be carried by absolute violence to bed. It's interesting that he was such a reluctant bather, given that a bed if given that a bed is the settle for the one story about him that everybody knows. According to the Roman architect Vitruvius, Archimedes becomes so excited by a sudden insight he had in the bed that he leaped out of the tub and ran down the street next shouting, Eureka! I have found it. Other stories cast him a military magician, a warrior scientist, one-man death squad. According to these legends, when his home city of Syracuse was under siege by the Romans in 20 212 BCE, Archimedes, then an old man around 70, helped defend the city by using his knowledge of polish and levers to make fantastical weapons, war engines, such as grappling hooks and giant cranes that could lift the Roman ships out of the sea and shake their sailors from them like sand being shaken out of a soul. A Plutarch described the terrifying scene. A ship was frequently lifted up to a great height in the air, a dreadful thing to behold, and was rolled to and fro, kept kept swinging until the mariners were all thrown out, but at length it was dashed against the rocks or let fall. In a more serious vein, students of science engineering remember Archimedes for his principle of buoyancy. A body immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced, and his law of the lever. Heavy objects placed on opposite sides of or a lever will balance if and only if their weights are in inverse proportion to the distances from the fulcrum. Both of these ideas have countless practical applications. Archimedes' principle of buoyancy explains why some objects float and others do not. It also underlies all the naval architecture, the theory of ship stability, and the design of oil drilling platforms at sea. And you rely on his law of the lever, even if unknowingly, every time you use a nail clipper of a crowbar. Archimedes might have been a formidable maker of war machines, and he undoubtedly was a brilliant scientist and engineer, but what really puts him in the pantheon is what he did for mathematics. He paved the way for the integral calculus. Its deepest ideas are plainly visible in his work, but then they aren't seen again for almost 2 millennia. To say he was ahead for his time would be putting it mildly. Has anyone ever been more ahead of his time? Two strategies appear again and again in his work. The first was his ardent use of the infinity principle to probe the mysteries of cycles, spheres, and other curved shapes. He always approximated them with rectilinear shapes made of lots straight, flat pieces, faceted like faceted like jewels. By imagining more and more pieces and making them smaller and smaller, he pushed his approximations ever closer to the truth, approaching exactitude in the limit of infinitely many pieces. This strategy demanded that he be a wizard with sums and puzzles, since ended up having to add many numbers of pieces back together to arrive at his conclusions. His other distinguishing stratagem was blending mathematics with physics. The idea, the idea, the ideal, the ideal with the real. Specifically, he mingled geometry, the study of shapes, with mechanics, the study of motion and force. Sometimes he used geometry to illuminate mechanics, sometimes the flow went in the other direction, with mechanical arguments providing insight into pure form. It was by using both strategies and with consummate skill that Archimedes was able to penetrate so deeply into the mystery of curves. Squeezing pie. When I walk to my office or go out with my dog for an evening stroll, the pedometer on my iPhone keeps track on how far I walk. The calculation is simple. The apps the app estimates the length of my stride based on my height and counts how many steps I've taken. Then it multiplies those two numbers together. The distance they travel equals stride length stride length times the number of steps taken. Archimedes used a similar idea to calculate the circumference of a cycle and to estimate pi. Think of the cycle as a track. It takes a lot of steps to walk all the way around. The path would look something like this. Each step is represented by a tiny straight line. By multiplying the number of steps by the length of each one, we can estimate the length of the track. It's only an estimate, of course, because the cycle is not actually made up of straight lines. It's made up of curved arcs. When we replace each arc by a straight line, we're talking a slight shortcut. And so the approximation is served to underestimate the true length of the circular track. But at least in theory, by taking enough steps and making them small enough, we can approximate the length of the track as accurately as we wish. Archimedes did a series of calculations like this, starting with a path made up of six straight steps. He, he began with a hexagon because it was convenient base camp for which to embark on the most arduous calculations ahead. The advantage of the hexagon was that he could easily calculate its perimeter, the total length around the hexagon. It's 6 times the radius of the cycle. Why 6? Because the hexagon contains 6 equilateral triangles, each side of which each side of which equals the cycle's radius. 6 of the triangle sides make up the perimeter of the hexagon. So the perimeter equals 6 times the radius. In symbols, P equals 6r. Then, since the cycle's circumference C is longer than the hexagon's perimeter P, we must have C greater than 6r. This argument gave Archimedes a lower bound on what we could call pi, written as the Greek letter pi, and defined as the ratio of the circumference to the diameter of the cycle. Since the diameter d equals 2r, the inequality c greater than 6r implies p equals c over d equals c over 2r greater than 6r over 2r equals 3. Thus hexagon argument demonstrates p greater than 3. Of course, 6 is a ridiculously small number of steps, and the resulting hexagon is obviously a very cool caricature of a cycle, but Archimedes was just getting started. Once he figured out what the hexagon was telling him, he shortened the steps and took twice as many of them. He did that by detouring to the midpoint of each arc, taking two baby steps instead of striding across the arc in one big step. Then he kept doing that over and over again. A man obsessed, he went from 6 steps to 12, then 20 to then 24, 48, and ultimately 96, 96 steps, working out the every shrinking length to migraine-inducing precision. Unfortunately, it got it got progressively harder to calculate the step lengths as they shrank, because he had to keep invoking the Pythagorean theorem to find them. That required him to calculate square roots, a nasty chore to do by hand. Furthermore, to ensure that he was always underestimating the circumference, he had to make sure that his approximating fractions bounded the bothersome square roots from below when he needed them to be underestimates, and from above when he needed them to be overestimates. What I am trying to say is that his calculation of pi was heroic, both logically and arithmetically. By using a 69 gun inside the cycle and a 60 gun outside the cycle, he ultimately proved that pi is greater than 3 plus 10 over 71 and less than 3 plus 10 over 30. 3 plus 10 over 70. Forget about math for a minute. Just suffer for this result at the visual level. The unknown and forever unknowable. The value of pi is trapped in a numerical vice, squeezed between two numbers and that look between two numbers that look almost identical except that the former has the denominator of 71 and the latter of 70. The latter result 3 plus 10 over 70 reduces to 22 over 7. The famous approximation to pi that all students still learn today, and that some are unfortunately mistake for pi itself. The squeeze technique that Archimedes used, building an aerial walk by the Greek mathematician Eudoxus, is now known as the method of exaltation because of the way it traps the unknown number pi, because the two now because the between two known numbers, the bounded tighten with each doubling. The bonds tighten with each doubling, then exalting the wiggle room for pi. Cycles are the simplest curve in geometry, yet surprisingly, measuring them, quantifying their properties with numbers, transcends geometry. For example, you will find no mention for pi in Euclid's Elements, written a generation or two before Archimedes. You will find a proof of you will find a proof by exhaustion that the ratio of a cycle's area to the square of its radius is the same for all cycles, but no hint that the universal ratio is close to 3.14. Euclid's omission was a signal that something deeper was needed to come to grips with pi's numerical value, required a new kind of mathematics, one that could cope with curved shapes. How to measure the length of a curved line, of the area of a curved surface, or the volume of a curved solid. These were These were the cutting-edge questions that consumed Archimedes and led him to take the first steps toward what we now call integral calculus. Pi was its first triumph. The Tau of Pi. It may seem strange to modern minds that pi does not appear in Archimedes' formula for the area of cycle A equals RC over 2, and that he never wrote down an equation like Z equal pi d to relate the circumference of a cycle to its diameter. He avoided doing all that because pi wasn't a number to him. It was simply a ratio of two lengths, a proportion between a cycle's circumference and its diameter. It was a magnitude, not a number. We no longer make this distinction between magnitude and number, but it was important in ancient Greek mathematics. It seems to have arisen from the tension between the discrete as represented by the whole numbers and the continuous as represented by shapes. The historical details are murky, but it appears that sometime between Pythagoras and Eudoxus, between the 6th and the 4th centuries BCE, somebody proved that the diagonal of a square was incommensurable with its side, meaning that the ratio of those two lengths could not be expressed as the ratio of two whole numbers. In modern language, someone discovered the existence of irrational numbers. The suspicion is that this discovery shocked and disappointed the Greeks, since it belied the Pythagorean credo. If whole numbers and their ratios could not even measure something as basic as the diagonal of a perfect square, then all was not number. This deflating letdown might explain why later Greek mathematicians always elevated geometry over arithmetic. Numbers could not be trusted anymore. They were inadequate as a foundation for mathematics. To describe continuous quantities and reason about them, the ancient Greek mathematicians realized they needed to invent something more powerful than whole numbers. So they developed a system based on shapes and their proportions. It relied on measures of geometrical objects, length of lines, areas of squares, volumes of cubes. All of these they called magnitudes. They could they thought of them as distinct from numbers and superior to them. This, I believe, is why Archimedes held pi at arm's length. He didn't know what to make of it. It was a strange, transcendent creature, more exotic than any number. Today, we accept pi as a number, a real number, an infinite decimal, and a fascinating one at that. My children certainly were intrigued by it. They used to stare at a pie plate hanging in our kitchen that had the digits of pi running around the rims and spiraling in toward the center, shrinking in size as they swirled into the abyss. For them, the fascination had to do with the random-looking sequence of digits, never repeating, never showing any pattern at all, going on forever, infinity on the platter. The first few digits in pi infinite decimal expansion are. We will never know. We will never know all the digits of pi. Nevertheless, those digits are out there, waiting to be discovered. As of this writing, 22 trillion digits have been computed by the world's fastest computers. Yet 22 trillion is nothing compared to the infinite of digits that define the actual pi. Think of how philosophically disturbing this is. I said that the digits of pi are out there, but where are they exactly? They don't exist in the material world. There exists in some Platonic realms, along with abstract concepts like truth and justice. There's something so paradoxical about pi. On the one hand, it represents order as embodied by the shape of a cycle, long held to be a symbol of perfection in eternity. On the other hand, pi is unruly, disheveled in appearance, its digits obeying no obvious rule, or at least none that we can perceive. Pi is elusive and mysterious, forever beyond reach. Its mix of order and disorder is what makes it so bewitching. Pi is fundamentally a child of calculus. It is defined as the unattainable limit of a never-ending process. But unlike a sequence of polygons steadfastly approaching a cycle of helpless worker stepping halfway to a wall, there is no end in sight of pi, no limit we can ever know. And yet, pi exists. There it is, defined so crisply as the ratio of two lengths. We can see right before us the circumference of a circle and its diameter. The ratio defines pi, pinpoints it as clearly as can be, and yet the number itself slips through our fingers. With its yin and yang binaries, pi is like all of calculus in miniature. Pi is a portal between the round and the straight, a single number yet infinitely complex, a balance of order and chaos. Calculus, for its part, uses the infinite to study the finite, the unlimited to study the limited, and the straight to study the curved. The infinity principle is the key to unlocking the mystery of curves, and it arouses her first in the mystery of pi. Cubism meets calculus. Archimedes went deeper into the mystery of curves, again guided by the infinity principle, in his treatise The Quadrature of the Parabola. A parabola describes the familiar arc of a three-point shot in basketball of water coming out of a drinking fountain. Actually, those arcs in the real world are only approximately parabolic. A true parabola to Archimedes would have meant a curve obtained by slicing through a cone with a plane. Imagine a mid-cleaver slicing to a dunce cap or a conical paper cup. The cleaver can make different kinds of curves depending on how steeply it cuts through the cone. A slice parallel to the base of a cone makes a cycle. A slightly steeper cut a slightly steeper cut produces an ellipse. A cut that has the same slope as the cone itself produces a parabola. Filled in the plane of the slice, the parabola appears as a graceful, symmetrical curve with a line symmetry down its middle. This line is called the Parabolas Axis. In his treatise, Archimedes set himself the challenge of working out the quadrature of a parabolic segment. In more modern language, a segment of a parabola means the curved region lying between the parabola and a line that cuts across its obliquely. Finding its quadrature means expressing its unknown area in terms of the unknown area of a simpler shape like a square, rectangle, triangle, or other rectilinear figure. The strategy used by Archimedes was astonishing. He reimagined the parabolic segment as infinitely many triangular shots glued together like pieces of broken pottery. The shots came in an endless hierarchy of sizes: one big triangle, two smaller ones, four smaller still, and so on. His plan was to find all their areas and then add them back together to calculate the curved area he was wondering about. It took a kaleidoscopic leap of artistic imagination to see a smooth, gently curving parabolic segment as a mosaic of jagged shapes. If he had been a painter, Archimedes would have been the first cubist. To carry out his strategy, Archimedes first had to find the areas of all the suns. But how, precisely, were those suns to be defined? After all, there are countless ways to piece triangles together to form a parabolic segment, just as there are countless ways to smash a plate into jagged bits. The biggest, the biggest triangle could like this or this or this. He came up with a brilliant idea. Brilliant, brilliant because it established as a rule a consistent pattern that held from one level of the hierarchy to the next. He imagined sliding the oblique line at the base of the segment upward while keeping it parallel to itself until it just barely touched the parabola at the single point near the top. That special point of grazing contact is called a point of tangency, from the Latin root tangere, meaning touching. It defines the third corner of the big triangle, the other two being the points where the oblique line cut the parabola. Archimedes used the same rule to define the triangles at every stage in the hierarchy. At second stage, for example, the triangles look like this. Notice that the sides of the big triangle now play the role of the oblique line used earlier. Next, Archimedes invoked known geometrical facts about parabolas and triangles to relate one level of the hierarchy to the next. He proved that each newly created triangle had one edge, as much area as its parent triangle. Thus we say that the first, biggest triangle occupied one unit of area. The triangle will serve as our area standard, then its two daughter triangles together occupy 1 over 8 equal plus 1 over 8 equal 1 over 8 plus 1 over 8 equal 1 over 4 as much area. At each subsequent stage, at, at each subsequent stage, the same rule applies. The daughter triangles always contribute a total of quarter as much area as their parents does. So the total area of parabolic segment reassembled from the whole infinity hierarchy of such must be an infinite series in which each term in one quarter of them preceding it. There's shortcut to sum this kind of infinity series, which is known in the trade as a geometric rules. The trick all is to cancel all but one of its infinitely many terms by multiplying both sides of the equation for area by 4 and subtracting the original sum for it, which, watch, multiplying each term by 4 in the infinite series above gives. The magic happens between the next to last line and the last line above. The right hand side of the last line equals 4 plus area, because the original sum area equals 1 plus 1 over 4, 1 over 1 over 16, etc. has, like a phoenix, been reborn in the terms following the 4 in the next to last line. So 4 times area equals 4 plus area. Subtract one area from both sides to get 3 times area equals 4. Thus, area equals 4 over 3. In other words, the parabolic segment has 4 over 3 the area of the big triangle. A cheesy argument, Archimedes would not have approved of the legerdemain above. He arrived at the same result by a different route. He resorted to a subtle style of argumentation often described as a double reductio ad absurdum, a double proof by contradiction. He proved that the area of the parabolic segment could not be less than 4 over 3 or greater than 4 over 3, so it must 4 over 3. As Sherlock Holmes later puts it, when you have limited the impossible, whatever remains, however improbable, must be the truth. What's, what's conceptually crucial here is that Archimedes eliminated the impossible with arguments based on a finite number of such. He showed that the combined area could be made as close to variability as desired, closer than any prescribed tolerance, simply by taking enough of them. He never had to summon infinity, so everything about his proof was ironclad. It still meets the highest standards of the rigor today. This gist of his argument becomes easy to understand if we put it in everyday terms. Suppose suppose three people want to share four identical slices of cheese. The common sense solution would be to give each person a slice, then cut the remaining slice into thirds and hand them out. That's fair. In total, everyone would get 1 plus 1 over 3 equals 4 over 3 of a slice. But suppose of three people happen to be mathematicians who are milling around the food table before the seminar, eyeing that last that eyeing that eyeing the last four slices of cheese. The cleverest of the three, coincidentally named Archimedes, might suggest the following solution. I'll take I'll take a slice and you guys take yours, which leaves one more for us to share. Euclid cut that leftover slice into quarters, not thirds, and everyone take a quarter of that leftover slice. We're going to keep doing this, always cutting what's left over into four equal portions, into the remaining crumb is of now if us is of no interest to anyone. Okay, Evdoxus to winning. How many slices of cheese total would each of them get to eat if they were to go on indefinitely? One way to look at it is to keep a running tally of how many slices each person gets. After round 1, each gets one slice. After round 2, when the cutter slices are passed out, each person has accumulated one over 4 slices. After round 3, when the cutters are themselves quartered into 16, the running total of each is 1 over 1 plus 1 over 4 plus 1 over 16 slices, and so on. Loosely speaking, each of the three people who eventually get to eat 1 plus 1 over 4 plus 1 over 16 slices in total if the cutting went off forever. And since this amount must represent a third of the original 4 slices, it must be that 1 plus 1 over 4 plus 1 over 16 equals 1/3 of 4 equals which is 4 over 3. In the quadrature of the parabola, Archimedes gave an argument very close to this, including a diagram with squares of different sizes. But he never invoked infinity of or used the counterpart of the three dots above to signify that the sum went on endlessly. Rather, he phrased his argument in terms of finite sums so that it was unimpeachably rigorous. His key observation was that the tiny square in the upper right corner. The current leftover remaining of to be set could be made smaller than any given amount when considering a sufficiently large but finite number of rounds, and by similar reasoning, the finite sum 1 over 1 over 1 plus 1 over 4 plus 1 over 16 plus etc. The total amount of cheese that each person gets could be as close could be could be made as close to 4 over 3 as desired by making n large enough. So the only possible answer was 4 over 3. The method. It's at this point that I begin to feel real affection for Archimedes because he does something in one of his essays that the few geniuses ever do. He invites us in and reveals how he thinks. I'm using the present tense here because the essay is so intimate. It feels like like he's speaking to us today. He shares his private intuition, a vulnerable, soft-bellied thing, and says he hopes that the future mathematicians will use it to solve problems that eluded him. Today, his secret is known as the method. I never had in calculus I never heard of it in calculus class. We don't teach it anymore. But I found the story of it and the idea behind it enthralling and astounding. He writes about it in a letter to his friend Eratosthenes, the librarian at Alexandria and the only mathematician of his era who could understand him. He confuses that even though even though his method does not furnish an actual demonstration of the results he's interested in, it helps him figure out God's truth. It gives him intuition, as he says. It is easier to supply the proof when we have previously acquired by the method some knowledge of the questions that it is to find it without any previous knowledge. In other words, by nodding around, playing with the method, he gets a feel for the territory, and that guided him to watertight proof. This is such an honest account of what it's like to do creative mathematics. Mathematicians don't come up with the proofs first. First comes intuition. Rigor comes later. This essential role of intuition and imagination is often left out of high school geometry courses, but it is essential to all creative mathematics. Archimedes concludes with the hope that there will be some among the present, as well as future generations, who by means of the method of the method here explained will be enabled to find other theorems which have not yet fallen to our share. That almost brings a tear to my eye. This unsurpassed genius, feeling the finiteness of his life against the infinitude of mathematics, recognized that there is so much left to be done, that there are other theorems which have not yet fallen to our share. We all feel that, all of us mathematicians. Our subject is endless. It humbled even Archimedes himself. The first mention of the method appears at the beginning of the essay on the quadrature of the parabola before the cubist proof with the shards. Archimedes confessed that the method led him to that proof and to the number 4 over 3 is in the first place. What is the method, and what is so personal, brilliant, and transgressive about it? The method is mechanical. Archimedes finds the area of the parabolic segment by weighing it in his mind. He thinks of the parabolic region as a material object. I'm picturing it as a thin sheet of metal carefully trimmed into the desired parabolic shape, and then he places it at one end of an imaginary balance scale. Or, if you prefer, think of it as being seated at one end of an imaginary seesaw. Next, He figures out how to counterbalance it against a shape he already knows how to weak, a triangle. For this, he deduced that the area of the original parabolic segment. It's an even more imaginative approach than the cubist geometry or such the cubist geometric saws and triangle techniques of his that we discussed earlier, because in this case he's going to build the imaginary seesaw as part of the calculation and design it to to comport with the parabola's dimensions. Together they will produce the answer he seeks. He starts with a parabolic segment and tilts it to ensure that the parabola symmetries the parabola symmetry axis is vertical. Then he built then he builds the seesaw around it. The instruction manual reads as follows. Drag the big triangle inside the parabolic segment as before and label it ABC. As in the cubist proof, the triangle is again going to serve as an area standard. The parabolic segment will be compared to it and will turn out to have four-thirds its area. Next, enclose the parabolic segment in much bigger triangle ACD. The triangle's top side is chosen to be a line tangent to the parabola at the point C. Its base is the line AC, and its left side uh, is a vertical line that extends upward from A until it meets the top side at point D. Using standard Euclidean geometry, Archimedes proved that this huge order triangle ACD has 4 times the area of the inner triangle ABC. The fact will become important later. See it aside for now. The next step is to build the rest of the seesaw, its lever, its two seats, and its fulcrum. The lever is the line that joins the two seats. The line starts at C, goes to B and makes from the huge outer triangle at F the fulcrum, and continues to left until it hits a point S, the seat. The condition that defines S is that it's as far from F as E is. In other words, F is the midpoint of the line SC. Now comes the stunning insight that underlies the whole conception. Using known facts about parabolas and triangles, Archimedes proved that he can balance the huge outer triangle against the parabolic segment if he thinks about them one vertical line at a time. He regards them both as being composed of infinitely many parallel lines. Those lines are like infinitesimally thin slats or ribs. Here, here's, here's a typical pair of them, defined by a single vertical line through both shapes. On that line, a short rib connects the base to the parabola, and a tall rib connects the base to the top side of the huge outer triangle. His amazing insight is that these ribs balance each other perfectly, like kids playing on a seesaw, as long as they sit in the right places. He proves that if he slides the short rib over to the point S and lifts the tall rib in place, they balance. The same is true for every vertical slice. No matter which vertical slice you take, the short rib always balance the tall rib if you slide the short rib to S and lift the tall rib in place. So the two shapes balance each other, rib by rib. All the ribs from the parabola end up at S. Together, they balance all the ribs from the huge order triangle ACD. and since those ribs haven't moved, that means all the parabolic mass shifted to S, balance the huge triangle right where it is. Next, Archimedes replaces the infinitely ribs of the huge outer triangle with an equivalent point of their own, called the triangle's center of gravity. It serves as a proxy. As far as scissors are concerned, the huge triangle acts as if its entire mass were concentrated at a single center of gravity. The location That location, Archimedes has already shown in other work, lies on the line Fc, at a point precisely 30 times closer to the fulcrum F than S is. So, since the entire mass of the triangle sits 3 times closer to the pivot point, the parabolic segment must weigh a third as much as the huge triangle in order for them to balance. That's the law of the lever. Therefore, the area of the parabolic segment must be one-third that, that of the huge order triangle ACD. And since that order triangle has 4 times the area of the inner triangle ABC, the fact we set aside earlier, Archimedes deduced that the parabolic segment must have 1 over 3 the area of the triangle ABC inside it, just as we found earlier by summing the infinite series of triangular shards. I hope I've managed to convey what an acid trip to an argument this is. Instead of a potter resembling shards, here Archimedes is more like a butcher. He takes the tissue of the parabolic region apart, one vertical strip at a time, and hangs all these infinitesimally thin strips of flesh from a hook at S. The total weight of all the flesh stays the same as it was back when it was an intact parabolic segment. It is just that he has added the original shape into lots of vertical stringy strips, all hanging from the same meat hook. It's such a weird image. Maybe we should stick with scissors. Why did I call this argument transgressive? Because it traffics with completed infinity. At one stage, Archimedes openly describes the other triangle as being made up of all the parallel lines inside itself. That, of course, is taboo in Greek mathematics. There's a continuous infinity of these parallel lines, these vertical ribs. He's openly thinking of the triangle as a completed infinity of ribs. In doing so, he's unleashing the golem. Likewise, he describes the parabolic segment as being made up of all the parallel lines drawn inside the curve. Dealing with the dealing with completed infinity lowers the status of this reasoning, in his estimation, to a heuristic, a means of finding an answer, not a proof of its correctness. In his letter to Eratosthenes, he downplayed the method as giving nothing more than a sort of indication that the conclusion is true. Whatever its logical status, Archimedes' method has an a pluribus unum quality to it. This Latin phrase, the motto of the US, means out of many one. Of the, invi- out of the infinitely many straight lines making up the parabola, one area emerges. Thinking of that area as a mesh, Archimedes shift it like line by line to the far left seat on the seesaw. The infinitude of lines is thereby represented by a single mass seated at a single point. The one replaces the many and stands for it, representing it perfectly and faithfully. The same is true for the counterbalancing outer triangle on the right of the seesaw. Out of its continuum of vertical lines, one point is chosen, its center of gravity. It too stands for the whole. Infinity collapses to unity, a pluribus unum. Except this is not poetry or politics. This is the beginning of integral calculus. Triangles and parabolic regions are apparently and mysteriously equivalent, in some sense that Archimedes could not quite make rigorous to infinitudes of vertical lines. Although Archimedes seems embarrassed by his dalliance with infinity, he is brave enough to own up to it. Anyone trying to measure a curved shape to find the length of its boundary or the area of the volume inside it has to grapple with the limit of an infinite sum or infinitesimally small pieces. Careful souls may try to sidestep the necessity, financing it with a method of exhaustion, but at bottom there is no escaping it. Coping with curved shapes means coping with infinity, one, one way or another. Archimedes is open about this. When he needs to, he can dress up his proofs in respectable garb, sporting finite sums and the method of exhaustion. But in private, he is dirty. He admits to wake he admits to waking shapes in his mind, dreaming of levers and centers of gravity, balancing regions and solids line by line, one infinitesimal piece at a time. Archimedes went on to apply the method to many other problems about curved shapes. For example, he used it to discover the center of gravity of a solid hemisphere, a a paraboloid, and the segments of ellipsoids and hyperboloids. His favorite result, which he loved so much that it be carved on his tombstone, concerned the surface area and volume of a sphere. Picture a sphere sitting snugly in cylindrical head box. Using the method, Archimedes discovered that the sphere has 2 over 3 the volume of the enclosing head box, as well as 2 over 3 of its surface area, assuming the top and bottom lids are also counted in the head box surface area. Notice that he didn't give formulas for the volume of the surface area of the sphere as we would today. Rather, he phrased his result as proportions. That classic that that's classic Greek style. Everything was expressed as a proportion. An area was compared to another area, a volume to another volume, and when the ratio involved a small and when the ratio involved small whole numbers, as they do here with 3 and 2, and as they did with 4 and 3 in the quadrature of the parabola, that must have been a source of particular pleasure to him. After all, those same ratios, 3, 3 over 2 and 4 over 3, had special significance to the ancient Greeks because of their central roles in the Pythagorean theory of musical harmony. Recall that when two otherwise identical strings with lengths in the ratio 3 over 2 are struck, they harmonize beautifully, separated in pitch by an interval known as a fade. Similarly, strings in a 4 over 3 ratio produce a fourth. These numerical coincidences between harmony and geometry must have delighted Archimedes. His word in his essay on the sphere and cylinder suggests just how tickled he was. Now, these properties were all along naturally inherent in the figures, but remain unknown to those who were before my time engaged in the study of geometry. I know how proud he sounds and focus instead on his claim that the properties he discovered were all along naturally inherent in the features, but remain unknown. Here, he is expressing a particular philosophy of mathematics dear to the hearts of all working mathematicians. We feel we are discovering mathematics. The results are there, waiting for us. They have been inherent in the figures all along. We are not inventing them. Unlike Bob Dylan or Toni Morrison, we are not creating music or novels that never existed before. We are discovering facts that already exist, that are inherent in the objects we study. Although we are, although we have such- we ha- although we have such creative freedom to invent the objects themselves, to create idealizations and circulars like perfect spheres and cycles and cylinders, once we do, they take on life of their own. When I read the way Archimedes expresses his pleasure at unveiling the surface area and volume of the sphere, I feel I feel like I'm feeling the same thing he felt, or rather, that he was feeling the same things I felt. That he was feeling the same things I feel. That and that all my and that all of my college feel when we do mathematics. Although we are told that the past is a foreign country, it may not be foreign in every respect. People we read about in Homer and the Bible seem a lot like us, and the same appears to be true of the ancient mathematicians, or at least of Archimedes, the only one who let us into his heart. 22 centuries ago, Archimedes wrote a letter to his friend Eratosthenes, the librarian at Alexandria, essentially sending him a mathematical message in a bottle that virtually no one could appreciate, but that he hoped might somehow sail safely across the seas of time. He had set his private intuition, his method, in the wish that it might enable future generations of mathematicians to find other theorems which have not yet fallen to our share. The odds we the odds were against him. As always, the effects of time were cruel. Kingdoms fell, kingdoms fell, and libraries were burned. Manuscript decayed. As not a single copy of the method was known to have su- survi- survived the Middle Ages. Although Leonardo da Vinci, Galileo, Newton, and other geniuses of the Renaissance and the scientific revolution poured over what was left of Archimedes' treatise, they never had a chance to read the method. It was thought to be irretrievably lost, and then miraculously it was found. In October 1998, a battered medieval prayer book came up for auction at the Christie's and sold to an anonymous private collector for $2.2 million. Barely visible under Barely visible under its Latin prayers lay faint geometrical diagrams and mathematical text written in 10th century Greek. The book is palimpsest. In the 13th century, its parchment folios had been washed and scraped clean of the original Greek and overwritten with Latin liturgical text. Fortunately, the Greek was not completely obliterated. It contains the only surviving copy of Archimedes' method. The Archimedes Palimpses, as it is now known, first came to light in 1899 in a Greek Orthodox library in Constantinople. It spent the Renaissance and the scientific revolution undetected in the prior book in the monastery of Saint Sabas near Bethlehem. It now lies in the Walters Art Museum of Baltimore, where it has been lovingly restored and examined using the latest imaging technology. Archimedes today, from computer animation to facial surgery. Archimedes' legacy lives on today. Consider the computer animated movies that our kids love to watch. The characters in films like Shrek, Finding Nemo, and Toy Story seem like lifelike and real in part because they embody an Archimedean insight. A smooth surface can be convincingly approximated by triangles. For example, here are three triangulations of a mannequin head. The more triangles we use and the smaller we take them, better the approximation becomes. What's true for the mannequins is equally true for ogres, clownfish, and toy cowboys. Just as Archimedes used a mosaic of infinitely many triangular shots to represent a segment of a smoothly curved parabola, modern day animators at DreamWorks created Shrek's round belly, and his cute little trumpet-like ears out of tens of thousands of polygons. Even more were required for a tournament scene in which Shrek battled local thugs. Each frame of that scene took over 45 million polygons, but there was no trace of them anywhere in the finished movie. As the infinite principle teaches us, the straight and the jagged can impersonate the curve and the smooth. When Avatar was released nearly a decade later in 2009, the level of polygonal detail become more extravagant. Director James Cameron's insistence. Animators used a million polygons to render its plant on the imaginary world of Pandora. Given that the movie took place in a lush virtual jungle that amounted to a lot of plants and a lot of polygons, no wonder Avatar can cost $300 million to produce. It was first movie to use polygons by the billions. The earliest computer-generated movies used far fewer polygons. Nonetheless, the computations seemed staggering at the time. Consider Toy Story, released in 1995. Back then, it took a single animator a week to sync an 8-second shot. The whole film took 4 years and 800,000 hours of computer time to complete. As Pixar co-founder Steve Jobs told Wired, there are more PhDs working on this film than any other in movie history. Soon after Toy Story came Gary's Game, the first computer animated film with a human main character. The funny sad story of a lonesome old man who plays chess with himself in the park won the 1998 Academy Award for Best Animated Short Film. Like other characters generated by a computer, Gary was built for angular shapes. At the beginning of this section, I showed a computer graphic of a face made for ever more triangles. In much the same way, the animators at Pixar fashioned by Gary's had from a complex polyhedron a three-dimensional gem-like shape that consisted of about 4,500 concerns with a with flat facet in between them. The animator subdivided those facets repeatedly to create an increasingly detailed depiction. This subdivision process took up much less memory in the computer than earlier methods had, and it allowed for much faster animations. It was a revolutionary advance in computer animation at the time, but in spirit it channeled Archimedes. Recall that to estimate pi, Archimedes started with a hexagon, then subdivided each of its sides and pushed their midpoints out to the cycle to generate 12 gon. After another subdivision, the 12 gon became a 24 gon, and then 48 gon, and finally 69 gon, each encroaching ever more closely to its target, a limiting cycle. Likewise, Gary's animators approximated the character's wrinkly forehead, his protuberant nose, and the folds of skin in his neck by repeatedly subdividing a polyhedron. By repeating that process enough times, they could make Gary look like what he was intended to be, a puppet-like character who conveyed a wide range of human feeling. A few later, a few years later, a, a Pixar rival, DreamWorks, took the next steps forward in realism and emotional expansiveness in the story of Smelly, gauchy, heroic ogre of Smelly, gauchy, heroic ogre named Shrek. Although he never existed outside a computer, Shrek seemed practically human. That why that was partly because the animators took such great care to reproduce human anatomy underneath his virtual skin. They built virtual muscle, fat, bones, and more joints. It was done so faithfully that when Shrek opened his mouth to speak, the skin of his neck formed a double chin. Which brings us to another field where Archimedes' idea of polygonal approximation has proved useful: facial surgery for patients with severe overbites, mis mis misaligned jaws, or other congenital malformations. In 2009, in 2006, the German applied mathematicians Peter Doiflat, Matthew Weiser, and Stefan Zachow report the results of their work using calculus and computer modeling to predict the outcomes of complex facial surgeries. The team's first step was to build an accurate map of patient facial bone structure. To do so, they scanned the patients with computerized tomography (CT) or magnetic resonance imaging (MRI). The result gave information about the three-dimensional configuration of facial bones in the skull, from which the researchers created a computer model of the patient's face. The model was not just geometrically accurate; it was biomechanically accurate. It comparated realistic estimates of the material properties of skin and soft tissues such as fat, muscle, tendons, ligaments, and blood vessels. With the help of the computer models, with the help of the computer model, surgeons could then perform operations on virtual patients similar how to pilot, fighters fighter pilots sharpen their skills in flight simulator. Virtual bones in the face, jaw, and skull could be cut, relocated, augmented, or removed entirely. The computer calculated how the virtual soft tissue behind the face would move and reconfigure itself in response to stresses produced by the face's new bone structure. The results of such simulations were helpful in several ways. They alerted the surgeons to possible adverse effects the procedures could have on vulnerable structures like nerves, blood vessels, and the roots of teeth. They also revealed what the patient's face would look like postoperatively, since the model predicted how the soft tissues would reposition themselves after the patient healed. Another advantage was that the surgeons could prepare better for the actual operations in light of the simulated results, results and the patients could make the better decision about whether to have the operations. Archimedes came in the researchers modeled the smooth two-dimensional surface on the skull with an enormous number of triangles. The soft tissue posed its own geometrical challenges. Unlike the skull, soft tissues form a fully three-dimensional volume. It fills the complicated space in the front of skull and behind the skin of face. The team represented it The team represented it by hundreds of thousands of tetrahedrons, the three-dimensional counterparts of triangles. In the image below, the skull surface is approximated by 250,000 triangles. They are too small to see, and the volume of small tissues consists of 650,000 tetrahedrons. The array of tetrahedrons allowed the researchers to predict how the patient's soft tissues would deform after surgery. Roughly speaking, soft tissue is a deformable yet springy material, a bit like rubber or spandex. If you pinch your cheek, it changes shape. When you let go, it returns to normal. Ever since the 1800, 1018, 1800s, mathematicians and engineers have used calculus to model how different materials stretch, bend, and twist when the outcomes of about 30 surgical reputes pulled or sealed in various ways. The theory is most highly developed in the more traditional parts of engineering, where it's used to analyze the stresses and strains in bridges, buildings, airplane wings, and many other structures made of steel, concrete, aluminum, and other hard materials. The German researchers adapted the traditional approach to soft tissues and found that it worked well enough to be valuable to surgeons and patients alike. The idea was this: think of the soft tissue as meshwork of tetrahedrons connected to one another like beads connected to elastic threads. The beads represent tiny portions of tissue. They are tied together elastically because in reality atoms and molecules in the tissue are linked by chemical bonds. Those bonds resist stretching and compression, which is what endows them with elasticity. During a veto operation, a surgeon cuts bonds in the virtual phase and relocates some of the bond segments. When a piece of bond is moved to a new place, it pulls on the tissue and the tissues it's connected to, which in turn pull on the neighboring tissues. The meshwork reconfigures itself due to effect of cascading forces. As pieces of tissue move, they change the forces they set on their neighbors by stretching or compressing the bonds between them. Those affected neighbors themselves readjust, and so on. Keeping track on all the resulting forces and replacements is a massive calculation that can be done only by computer. Step by step, an algorithm updates the myriad of forces or moves the tiny tetrahedrons accordingly. Ultimately, all the forces balance and the tissue settles into its new equilibrium state. That's the new shape of the patient face that the models predicts. In 2006, Doiflat, Weiser, and Sarko tested their models' predictions against the clinical outcomes of 30 surgical cases. They found that the model worked remarkably well. As one measure of its success, it correctly forecast to within 1 millimeter the position of 70% of the patient's facial skins. Only 5 to 10% of the skin surface defeated by more than 3 millimeters from its predicted postoperative location. In other words, the model could be trusted, and it was certainly better than guesswork. Here's an example of one patient before and after surgery. The four panels show his profile before the operation far left, the computer model of his face at the time mid left, the prediction outcome of the surgery mid right, and the actual outcome far right. Look at the position of his jaw before and after. The result speaks for themselves. Onward to the mystery of motion. I am writ- I am writing I am writing these words today after a blizzard. Yesterday was March 14th, Pi Day, and we got over a foot of snow. This morning, while I was shoveling my drive away for the fourth time, I watched jealously as a small tractor with front-mounted snow thrower made its way easily down the side across the street. It used a rotating screw blade to pull snow into the machine and then ejected it onto my neighbor's yard. This use of rotating screw for propelling something goes back to Archimedes, at least according to legend. In his honor, today we call it an Archimedean screw. He is said to have come up with the invention during a trip to Egypt, although it may have been used much earlier by the Assyrians. It was developed to lift water from a long-lying area to an irrigation ditch. Today, cardiac assist devices use Archimedes screw pumps to support circulation when the heart left ventricle is impaired. But apparently, Archimedes did not want to be remembered for his screws or, or his work engines or any other practical inventions. He never left us any writing about them. He was proud of his inventions in mathematics, which also gets me thinking that it is fitting to be on his legacy on Pi Day. In the 22 years in the 2200 years, Archimedes tried pi. Numerical approximation to pi have been improved many times, but, but always by using mathematical techniques that Archimedes himself introduced, approximation by polygons or by infinite series. More broadly, his legacy was the first principal use of infinite process to quantify the geometry of cube shapes. Yet, the geometry of curve shapes takes us only so far. We also need to know how things move in this world, how human tissue shift after surgery, how blood pressures, how blood flows to an artery, how a ball flies to the air. On this, Archimedes was silent. He gave us the science of statics, of bodies balancing on levers and floating stably in water. He was a master of equilibrium, the territory I had concerned, the mysteries of motion.